Science 20s, it's Mr. Riley here. I figured you missed my face, so I decided to put my face back on the video. We're in the workbook on page 10, and we're looking at uniform motion. So that is a motion where you're not speeding up and you're not slowing down. You're traveling at a constant velocity. This is kind of where we left off before everything happened. We're looking at doing some graphing. And so what we want to look at is some of the reasons why we bother graphing in the first place. One of those things is graphing is going to allow us to communicate or even find a relationship between two different variables. So whether that's time and velocity for us, or maybe it's time and displacement for us, it can help us find the relationship between two different things. Another thing we use graphing for is to make predictions. So we can do what's called extrapolate data, and we can make predictions about things that might have happened before or after we were making observations. And then finally, we can actually take this relationship that we learn about and we can put it into mathematical context and put it into a mathematical expression or an equation. So a couple type of graphs that we're going to be looking at here mainly are a velocity time graph and a position time graph. And we're going to be looking at our graphs with time as the manipulated variable. So time is always going to go on the x-axis for us. And so if I'm looking at an object that is moving at a constant velocity, it's not speeding up. So if I'm looking at a velocity time graph for that object, this graph is going to be moving straight across. Now, if I'm looking at displacement or how much ground is covered over time, if I'm traveling at any velocity at all, I'm going to see a trend moving upward like this. Now, this would be if I'm moving forward. So these, this is something that's important for us to have in the back of our head. So moving on to the next page, page 11, we look at two examples of this. So for this first example, and I understand you guys went over this one in class as well, we're looking at an object that is moving at a constant velocity. So again, when we put this into a graph, this object is moving 2 meters per second every second over a course of 10 seconds. So if I'm going to graph this, it's going to look something like this. Oops. Something like this. And what this tells me is I have an object that's traveling at a constant velocity. The velocity is not changing. It's not going up or going down. It's not increasing or decreasing. Now, we can actually use some math with this graph as well. We can actually look at the area underneath the graph. So if I was to take my highlighter, and I'm just going to highlight all the area that's underneath this graph, it makes a square. And how do I find the area of a square? Base times height. And since my base is my time and my height is my velocity, then I'm going to actually end up with this formula right here. Velocity times time equals distance. So if I multiply 10 seconds times 2 meters per second, I'm going to get 10 times 2 is 20 meters. So the area under this graph will actually tell me my displacement. So I traveled for 2 meters per second for 10 seconds. I traveled 20 meters. Now, that's a velocity time graph. Let's look at a displacement time graph. So in a displacement time graph, my data table is going to look a little bit different. If I'm traveling at a constant velocity, I'm going to notice that my distance or my displacement is going to be increasing over time. So if I was to graph this, I would find that it would look a little something like this. And if I want to be proper, I'm going to circle my data points. And then for this type of graph, usually in an experimental setting, I would create what's called a line of best fit. So I would put a straight line in there. Let's see, can I figure out how to do this? Here you go. I put a straight line in here that's going to follow the trend of my data. Now, in this case, it's not really an experiment. All the data lines up perfect like that. Now, this straight line, I can use this mathematically to find something as well. And so what I want to actually calculate is the slope of this line. So for this instance, if I want to find my slope, what I'm going to do is I'm going to find two data points on here, and I'm going to create a little triangle. And to calculate the slope, I'm going to need to find the rise and compare that to the run. So what's my change on the y-axis, my displacement, compared to what's the change on my x-axis, which is my time. And this slope formula is on page 1 of your data booklet. Okay, and I know some of you guys in math class, you're familiar with calculating slope. Some of us it's a little bit tougher. So I'll help you out here. So the change in my y, so we got that delta, that means change in. The change in my y value is going to be y2 minus y1. So what does that mean? Well, in my triangle here, my lowest y value is going to be right here. And that happens to be, these are going up by 2s. So that's going to be 8. And so I'm going to have, that's going to be my y1. And my highest y value is going to be 10, 12, 14, 16. So 16 minus 8. So this rise right here represents 8 meters. And for my x value, my run, okay, I'm going to take my highest x value, which is going to be 5, 6, 7, 8, subtract 1, 2, 3, 4. So 8 minus 4 is going to be 4. And on my x, I'm dealing with seconds. So I'm going to have 4 seconds. So if I do my rise over run, it actually is displacement divided by time. So 8 meters divided by 4 seconds is going to give me my velocity. So for this type of graph, for a displacement time graph, the slope of your graph is your velocity. And I think we already know our velocity is going to be 8 divided by 4, which is 2 meters per second. So meters over seconds. So there's our velocity. Okay. So hopefully that helps you guys out. What I would like you to do is page 13, page 14, and page 15 for practice. And there's also a quiz on Google Classroom that I want you to take care of. And thanks for looking up my nose. I knew this camera didn't work very well. We'll talk to you guys next time.